Hi everyone, and welcome to this episode of the show. Today we have Mathieu Bozzio with us, who will be talking about a quantum weak coin flipping protocol that he and his colleagues developed. These kinds of protocols will potentially replace existing weak coin flipping protocols that are leveraging classical hardware. There's a lot of details to get into and that we will get into in the discussion, so I hope you enjoy it. So Mathieu, thank you very much for joining today.
Thank you.
So I figured we could kick this off by just giving a brief overview of the field. So we're going to be discussing quantum weak coin flipping. And if you want to introduce what the need is for those kinds of protocols and where they arise from.
Sure. So quantum weak coin flipping is just one example of a protocol that from the broader field of quantum cryptography. And basically in quantum cryptography, what you're trying to achieve is security guarantees that are stronger than what you have in classical cryptography. And how do you achieve these extra security guarantees or stronger security guarantees? This is by basically using the laws of quantum mechanics. And so by exploiting, for example, the no-cloning theorem of quantum mechanics, which basically says that you cannot clone an unknown quantum system without introducing any error. By using these fundamental principles, you can prove some security guarantees that essentially do not rely on the computational power of your adversary. So basically, even adversaries that have unlimited computational power cannot crack your protocol or cannot succeed in cheating in whatever protocol you're implementing. So that's kind of the broad context. Yeah.
Okay. And specifically now with the weak and strong coin flipping primitives that we're focusing on in this paper, do they have a specific correspondence in the classical cryptography space, or are these new ways of securing information that have not existed before?
No, they're actually they actually come from the classical setting. So classically, communication networks or some of the tasks that you do online are actually secured by these primitives, by coin flipping, bit commitment, oblivious transfer. So these exist classically. Only the only problem that you have is that these are based on some form of computational assumptions, or usually in some form of hashing that is vulnerable to these, let's say, computational attacks. So they do exist in the classical world. We're just proposing a way to make them secure against these attacks in the quantum world.
Mm-hmm. Okay, and we'll get into the protocol in just a second, but before we do, maybe you could describe the principles of quantum mechanics that are specifically involved here in the protocol that we will be discussing. The reason why we're now able to create a more secure weak coin flipping protocol, is that due to entangling in photons, or is it something else?
You can see it in different ways. I mean, in our protocol and implementation, we do have some form of entanglement in photon numbers. So we sort of entangle the 0 photon with the 1 photon components of the single photon that we send. But I prefer to see it maybe as here specifically exploiting single photon interference, which is really a quantum process in which you send a single photon in a large interferometer. And even though you have a single particle and a single photon, you can kind of see it as splitting through both parts of the interferometer, or at least its wave function split through both parts of the interferometer, and then you recombine them at the end. And whatever has happened on the way is detectable thanks to this single photon interference mechanism, and that's kind of how you can detect a cheating party, if this makes sense.
Yeah, no, absolutely.
So quantum interference here would be the main property problem. Yeah.
Right. And the last thing before we get into the protocol, there are a couple of concepts that you're discussing when it comes to this particular protocol. I'm specifically referring to fairness, correctness, and balancing. Could you quickly introduce those concepts, what they are, because I think we'll revert to them when we look at the results later.
Yes, sure. So the protocol of coin flipping or weak coin flipping in general just involves two parties who do not trust each other, and they basically attempt to flip a coin and to make a decision The point is they want opposite outcomes. So they're both going to try to cheat in some way or to bias the outcome of the flip in some way. And all these properties sort of describe what we want out of this protocol. So mainly the correctness just refers to the protocol working correctly when both parties are honest, so that if both parties do not try to cheat, the protocol actually succeeds with a high probability. The fairness is essentially saying that the coin flip should be fair, that is, both parties have equal probabilities of winning, which is what you want. You want a fundamentally unbiased random number in the end. And what we call the balance is basically the cheating probabilities when one of the two parties is dishonest. So if a protocol is balanced, a weak quantum flipping protocol is balanced, this would mean that the two cheating probabilities are equal. And of course, this wouldn't be 50-50, otherwise there would be no cheating. But this could be, for instance, 70%. This would be a balanced protocol where both parties can cheat at most with probability 70%, for example. So this, yeah.
Okay, so let's actually look at the protocol now. So I have it here, sharing it on the screen, and we have 3 stages of the protocol. So there's first the preparation stage, decision stage, and then verification. If we begin from the beginning, so with the preparation stage, can you quickly describe what happens in that stage conceptually?
Yes, so that stage is actually very simple. You generate a single photon. So ideally, this would be a perfect, pure single photon. And you send it on this beam splitter. A beam splitter is basically a semi-reflective mirror that will transmit the photon with some probability and reflect it with some other probability. And here these probabilities are given by x. So basically I send a single photon onto this x beam splitter, and this photon has some probability x of being transmitted and some probability 1 minus x of being reflected, for example. That's the preparation.
Mm-hmm. And when we think about the protocol here, do we consider it from the context of a single photon with sort of the particle assumption, or are we looking at the wave function of this? So we're going to get to, I guess, the interference of the photon with itself later, but do you mix between the two concepts when we're talking about this, or can you stick sort of throughout the entire protocol with one concept in mind?
That's a good question. Both visions are kind of necessary. I mean, of course, when I say that we send a single photon, and when I talk about it as being reflected or transmitted, you kind of think of it as a particle, right? That has some probability of going to this path or this path. However, as soon as you talk about interference, you think more about waves usually. So, and this single photon interference is just a phenomenon that happens also in the classical world with waves. But here it's going to be this kind of wave function of the single photon interfering with itself. So the path difference that you're going to have in the interferometer will influence your interference. And here it's probably nicer to reason in terms of wave. But that's the kind of duality of quantum. Yeah.
Okay. So the principle, the reason why I'm asking that now is when we transition now to the decision stage. So we initiate the photon here, send it through, and it makes it to Bob, essentially, who's at the decision stage. He has another splitter, and he also measures the photon that potentially passes through here. Will he always measure something, or is that dependent on whether the photon from a particle perspective actually makes it through?
That's exactly what you're saying. So basically, he will not always detect a photon because, as you say, from the particle behavior, if you kind of ignore the interferometer or you do not close the interferometer at the end, you can just see it as, well, the photon will just click at Bob's detector with probability x. And with probability 1 minus x, it will never click. So and it will go it will go to the other spatial mode, basically.
How come it's 1 minus x there? Is it not like 1 minus sort of x times y? I'm not sure if that would be the correct one now, but it passes through two.
Yes.
Right? Like
yes. I was simplifying. Yes. No, for sure. Here you have two beam splitters, so you'll get a product of probabilities. Yes. Yep.
Okay. Oh, cool. So sometimes Bob measures a photon, and I guess that plays a role in whatever the final outcome is going to be. So I'm trying to understand what we're going to get to in the end, which is the two different outcomes depending on what we measure with the final detectors here and how they relate to whether or not a party is cheating or not. But okay, so we detect a photon here with some probability. Bob then sends this to Alice again in this stage, and then there's a final interferometer here, Z. Can you explain the purpose of that one? So how do we get now from Bob having measured the outcome here to actually an outcome that we can measure and determine if one of these parties is cheating?
Yes. I think the best way to understand this last beam splitter is if you somehow replace this Y beam splitter, the decision beam splitter, by just a perfect mirror. If you just replace this by a perfect mirror, you essentially have an interferometer in the classical sense, right? You split and then you recombine. So this last beam splitter that you're talking about, the Z one, is just basically the closing part of the interferometer. And so if you somehow, for now, ignore what's happening on the Y beam splitter and just see it as a perfect mirror, what you have here is interference. And if everything goes well during the protocol, from the single photon interference properties, you should always get a deterministic outcome on this Z beam splitter. And for example, the deterministic outcome, if everything goes well, would be you always get a click on detector V1, but you don't get a click on detector V2. Or the opposite, you can design it whichever way you want. But the point is, as soon as you're going to get no clicks at all, or a click on the wrong detector, then you know something has gone wrong in the protocol, and that someone is probably cheating.
Okay, so let's try and link this now to the measurement outcomes that Bob might get. So in principle, the way this is split out, like the protocol, is either whether Bob measures a 0 or a 1. We talked about the case where an actual photon makes it through the first beam splitter here, and where Bob can measure it. How does that play a role for the final outcome? So depending on whether or not Bob gets a 0 or a 1, why does that matter for the final result?
This outcome is actually the crucial outcome of the protocol, in the sense that it's the outcome that gives you the coin flip. So basically, if Bob does not detect any photon at this step, so B equals 0, as you see on the figure here, well, the flip basically tells everyone that Alice has won. So he has to declare Alice as the winner of the protocol. If Bob gets a photon or detects a 1, he knows that Bob or himself has won the protocol. So this is really the actual outcome of the coin flip. Everything that comes after that is verification that parties are not cheating, basically. So that's what this step is here for. Yeah.
Okay. If we talk about how the parties would cheat in this case, from a conceptual basis, we'll talk about how you can detect that in the results that you observed as well, but just from a strategic perspective, like let's say you're Bob and you want to cheat, what would be your strategy in that case?
So in the case of Bob, we always claim that the strategy is pretty simple from the structure of the protocol. As you see, it's not a symmetric protocol because Bob is always the one declaring the outcome. So if you think in terms of, I want to basically boost my probability of winning as Bob, the coin flip, I will just always declare myself as the winner. That's my optimal strategy. It's not even a quantum strategy. It's literally just saying always the outcome is 1, I won. And that's how you increase your chances of winning as Bob.
And how is the protocol addressing that from a mitigation of, like, cheat mitigation perspective?
So that's when you have to consider, of course, the whole setup again for verification. So let's say that Bob cheats, so he declares himself the winner when he did not actually receive the photon. Well, as you know from our previous discussions, this means that the photon has actually gone through the other path. And the point is, if Bob declares himself the winner, then he will allow Alice to verify that he's not cheating. And what Alice will do is she'll check if she gets a photon on her detector. If Bob claimed that he was winning, this means that Alice should not get any photon on her detector. If she does get a photon, she knows that Bob was actually lying about winning the protocol. If that makes sense.
Okay, I want to look at the results. Yeah, exactly. I want to look at the results for that in a second. Maybe we can talk about Alice's cheat strategy before we actually start looking at those results. So if we do the exact same question, but we target it to Alice instead, how would she approach it differently if she wanted to cheat and do it optimally?
So as you see here, Alice's strategy will have to be quantum somehow. She will have to send some other quantum state than this single photon to somehow bias Bob into declaring her as the winner. And as we actually mentioned in the paper, what we have in our security proof is a mathematical upper bound on the cheating probability of Alice, which says that her optimal attack will never be higher than this. But we don't actually have an explicit attack that Alice can do. We just know that she can't cheat with probability higher than the number some number that's dependent on the experimental parameters. So what we do in the paper is we still illustrate some of the attacks that Alice can do, but we just know that that's not her best attack. And what she can do, for instance, is simply send or not send the photon to Bob with some different probability than X. She can just basically change the X. And of course, you see that intuitively, basically if Alice doesn't send anything to Bob, she has more chances of winning because Bob declares her the winner if he detects nothing. But of course, then she can get caught at the verification step later. And so basically her optimal attack will involve some form of optimization of this X parameter in order to win. It could also involve sending more photons or less photons, and that's kind of what the security bound takes into account. But that's just one example of an attack that Alice can do, which is not her best attack, but yeah.
Mm-hmm. I think for the results on Alice, it will also be important to discuss sanctioning. So maybe if we take a quick detour to that before looking at the results graph. You have a sanctioning parameter delta in your equations that you derived and in your graphs as well. Can you describe what that sanctioning actually does? Like what parameter do you set and how does that influence the protocol?
The sanctioning is essentially here. If you consider the protocol in some kind of larger framework, the point is the protocol is cheat sensitive, but with some probability it will not detect any of the two parties cheating, even if they do cheat, with some probability. And the point of this sanctioning is to essentially discourage any of the two parties from cheating. So they know that when they cheat, they have a small probability or large probability of getting detected. And if a sanction is imposed, probably also a sanction that could depend on the strength of the cheating, then they will be deterred or discouraged from cheating. So this is why we kind of introduce this parameter as some kind of extra component of the protocol. The protocol works without this parameter. Only there, someone can still cheat without being detected with some probability.
What I'm showing now is the graph that illustrates the probabilities of Bob winning or being sanctioned when he's performing an optimal attack. So if you could just summarize this graph, I think it's better if you do it than if I do it.
Yes. So here you picked a graph that actually depends on the distance between the two parties. And in experiment, distance actually means losses. So as you increase the distance, you have more chances of losing the single photon that's somewhere in your setup. So here we just wanted to show that the probability of Bob winning decreases as a function of distance, or basically decreases as a function of increasing losses, and that his sanction probability also decreases. Basically, that's just essentially what this graph shows. We care about this distance and we care about these losses because if you're going to do any realistic implementation of this protocol, it has to take into account all these imperfections of the real world, basically. Of course, in an ideal protocol, these don't play a role. You have no losses, and then these probabilities would behave differently. But here, this is some kind of illustration of the real setup.
Okay. If we look at the numbers on this graph, like if we look at the sanction probability, that's around 10% or lower, and the winning probability is around 90%. If we compare that to classical systems that exist now, what are their ranges between? So when I saw this graph, my first impression is, okay, if there's a 90% probability that you can cheat using an optimal cheat strategy and still win, essentially, that protocol needs to have fundamental changes before it would be sort of applicable in the market. Yes, exactly. Maybe that understanding is wrong. I don't know what current protocols are, but do you have a sense of what the winning probability would need to reach before this would be sort of viable from a commercial perspective?
That's a very good question, and it all kind of boils down to what you use the protocol for. To answer the first part of your question, this sort of cheat sensitivity is something that we really claim exists only in the quantum world. So what you would get classically is you would get a protocol where, under some security assumptions, the parties cannot cheat at all. But this comes under the assumption that we mentioned at the start of the session, that basically the parties do not have some kind of large computational power, so that they cannot break the hash function, for example, that's used in the implementation of the protocol. So if you're okay with this, and if you assume this classically, and you say this is secure, then the winning probability, the cheating probability of both parties is basically 50%. It's the kind of ideal probability that you want. And there is no need for cheat sensitivity because no one can actually cheat. What happens in the quantum world and why we have these numbers is that we're in some kind of new form of security where you do not need this assumption of computationally bounded adversaries, for example. Everything is secure thanks to the laws of the universe. However, we cannot lower this cheating probability arbitrarily close to 50%. In the ideal world without losses, this is actually possible for quantum weak coin flipping. But as soon as you start having imperfections, it's very hard to lower this probability all the way down to 50%. So then that's why we introduce the cheat sensitivity, which quantum gives you. And that's why you really have to think about where you use your protocol. If you're using your weak coin flipping protocol as a primitive, which means that you're usually going to use it as a black box to construct less basic primitives and then to construct applications, this might not be extremely useful if you have these finite numbers. However, if you treat your protocol as a whole and as an end in itself, that, for example, you want an outcome of the protocol and then whatever you're doing stops here, then these probabilities don't have to be arbitrarily low. As soon as you can detect someone cheating, that's what you want. And in that case, as an application that I like citing for weak coin flipping protocols in general, there would be these kind of randomized leader election protocols that you get in some cryptocurrencies, for example. That when a lot of parties who don't trust each other have to elect a new leader, that is a version of coin flipping. And if you do this without constructing anything on top, and you can detect cheating parties, then this is actually quite a useful protocol. So I hope this is clear.
Yeah, sure. One consideration I had, I think there's a reference to this in the paper as well. So if we bring this back to the correctness condition, I think you could enhance the sanction probability if you allow the protocol to infringe on the correctness condition. Is that true, or is that understanding incorrect?
So you mean if you compromise a little bit on the correctness or maybe the fairness, that then you could have higher cheating probability, for example? Is that what you're asking? Sorry, exactly. higher sanction. Yeah.
Exactly. So you have the condition now that you should never sanction Alice or Bob whenever they're not cheating, right? And what I'm asking is, if you relax that criteria a bit, like you incur a probability that, okay, we won't actually sanction them with a probability exceeding 0.5% or whatever, given that they follow, that they're honest, would that potentially improve this?
Yes, this would probably increase the cheat sensitivity properties, for example. In the end, as you see, the whole protocol is kind of parameterized by X, Y, and Z. So any kind of optimization and any kind of trade-offs that you do between these parameters can boost some of the properties. In the end, at least in the quantum field, we care a lot about not sanctioning honest parties, because otherwise the protocol is a bit, dangerous to get into. So that's why we fixed the parameters such that the correctness and the fairness are unity or 50%. But of course, by making trade-offs, if you have an application where that's not so much of a problem, then you can, of course, boost the other properties. It's just very application focused, I would say. application dependent. Yeah.
Yes, cool. So let's move over to Alice now. So the two graphs I have here illustrate the results that you get when Alice sends a different value for x than the honest one. Can we maybe start with the left graph, if you would just explain what that one illustrates?
Yes. So here on the x-axis you have the value of x that a dishonest Alice would actually be changing. So here we tune x over almost its full range, and we show how the other parameters of the protocol evolve when Alice cheats in this way. And so what you can see from the green curve, for example, is that it's not so trivial for Alice to cheat. There is some kind of optimal point where her cheating strategy is somehow the highest, and then it kind of drops again. So this green curve tells you, as a dishonest Alice, if you're going to implement this strategy, probably your best chance of winning would be around here 0.8, x equals 0.8, for example. Then you see that the chance that Bob wins, of course, decreases. If Alice has more chances of winning, then Bob usually has less chances of winning. And then we actually also plotted the red curve, which is the probability that Alice gets sanctioned when she cheats. And this is when this kind of same old story of game theory kind of comes into play, that depending on the sanction, Alice would or would not dare implement these cheating strategies. So then it's always a trade-off between does she mind getting caught cheating? Would she rather cheat less but have less risk of being sanctioned? So these curves show this trade-off a little bit as a function of x.
Mm-hmm. Okay, and I assume that if you were to sum the red and the green one, they would amount to also a linear a curve going upwards, like that opposes the curve that you see for Bob, or okay.
Yes, here you have to somehow normalize. I mean, you have to take into account the probability that the protocol aborts in these curves before making any conclusion on the sum of the curves. So this I would just have to remember how we actually normalized the curves here. But in the ideal case, they should add up to 1, but you have to take into account that the protocol also simply fails with some probability.
Okay.
Yeah.
Can we make a small excursion and talk about that as well? So, under which circumstances would the protocol actually abort, and how do you? What's the purpose of having that functionality as part of the protocol?
The abort functionality. You mean why do we have it? The abort functionality is really something that we do not want to have. It's just that we have it because we live in the real world where photons get lost very easily, and also where the visibility of your interferometer is not perfect. So this abort probability just states the probability that some of the one outcome occurs on the detector, so some pattern of clicks occurs that does not indicate anything. So you can't necessarily infer from that someone is cheating, that someone is winning. It's just something that the experiment gives you that you cannot really work with. And of course, we can design the protocol such that it's robust to these things. But there are conditions where, for example, no one detects any clicks. This could be problematic because no one knows where the photon went. It's hard to tell if someone was cheating. So that's kind of a very easy example to understand why this abort is not 0 in the imperfect case. For example, if the photon gets completely lost and you have absolutely no clicks on any detector, then it's hard to conclude something from this.
Mm-hmm. Okay, understood. Is that always easily detectable? Like, can you always distinguish when something goes wrong, if it goes wrong, or do you sometimes have a bleed where something really goes wrong in the protocol, but that does not necessarily result in the protocol aborting?
This should not happen. So if something goes wrong, and this is not some kind of abort pattern that you've pre-agreed on, this must mean that one of the parties is cheating, essentially. So if I understand your question correctly, there are some patterns where we know beforehand that, okay, this we cannot conclude anything, but all the other patterns that we mention will fall under one of the categories winning, cheating, either Alice or Bob. Yeah.
Mhm. My question on that is not so much whether they fall into the categories, but whether you know that everything that falls into the category actually is accurate. So you had the notion of correctness before that says you won't sanction Alice unless she's actually cheating. Could you have some form of scenario where the inefficiencies or suboptimalities of the protocol make it such that it looks like Alice was cheating even if she's not? Like, do you still have some perhaps negligible but nevertheless existing probability of that happening?
That yes. In experiment you have you have losses, but you also have imperfections of the detectors that detect the photons, and these detectors have dark counts sometimes. Dark counts are basically detections that occur when no photon has actually impinged on the detector. It's due to the intrinsic way that the detector works and the photons that are basically already inside the detector, if you want to see it like this. So sometimes a detector can click when actually no photon from the outside was coming in, or some noisy photon that wasn't meant to be part of the experiment. In some cases, if there's a dark count and the actual photon of the experiment gets lost, the one that we care about, this can lead to a party being called a liar or a cheater, even if they were honest. However, for example, in the case of dark counts, this is so low these days because the quantum technology is really the detector technology is getting very impressive, that we assume it's negligible. But with some very, very small probability, you could be caught cheating even if you were honest, with dark counts, for example.
Mm-hmm. Okay,
yep.
Understood. So great, let's focus on the next graph, which is on the right-hand side. Maybe you can summarize the plot first yourself, and then I can ask some questions as a follow-up.
So the plot just follows the plot from the left, basically, that we're, again, varying the x parameter that Alice plays with, dishonest Alice plays with. And then we're plotting here the deterrent factor, so how, let's say, important the sanction would be if Alice gets caught. And then on the left, we have the scale for Alice's interest function.
My thought process is we have some deterrent factor, and what is that, conceptually speaking, telling us? Is it like let's say you have Alice winning, and that gives you 1 point. Let's say, I don't know if that's how you count. Is the deterrent factor sort of a minus 1 point, and what you change with the deterrent factor is the severity of that penalty, or how do you think about the deterrent factor?
So that's a very good question. It's very dependent on the theory that you use. What you're actually saying would be a totally valid way of doing things, right? You get some points, some amount of points for winning, and you get some penalty for being caught cheating. And of course, as delta increases, this penalty is larger. And in the end, you kind of want to maximize your gains, right? So it's going to be some trade-off between these two. That's probably actually the most natural way of seeing it. Then I'm not very familiar with game theory, so I'm very confident that there's a lot of other ways of modeling it, depending on the scenario that you're in. But I think the way that what you mentioned is probably the most intuitive way of seeing it. Yeah.
Mm-hmm. Okay. But regardless of what the actual equation is then for the interest function, I guess the conceptual takeaway from this graph is that when we don't have any deterrent factor in this protocol, naturally there's a tendency for Alice to try and cheat all the time. But then as you include that, you have some form of optimum where there's a trade-off between trying not actually to get caught in cheating and, cheating enough so that you are often successful.
Exactly. Yep. That's really, it's a very simple idea in itself. It's just that we thought it was a very important idea to put in there, just to make the protocol more interesting for applications, basically. That, of course, you allow the parties to cheat successfully with some probability, but they also have this sanction that can stop them from trying to cheat too much. Yeah.
Mm-hmm. Mm-hmm. If we think about next steps in terms of research as a follow-up to the things that you've now done, what would you say are natural progressions of this? Was there anything you found in the research where you thought, okay, this part needs further work? Do you know of any other people that have done similar experiments since and that have come to different conclusions? Is there anything like that you think would be useful for you to investigate further in the future?
Yes, so regarding the weak coin flipping primitive specifically, right? There has been no other experiment. This was actually the first one, and since it's very recent, I think no one has had time to perform another experiment yet. But there are definitely things to consider. For example, of course, this cheat sensitivity is a very nice thing, and this deterrent factor that we introduced in order to compensate for this finite probability of cheating that's not zero. Of course, ideally, you would want a protocol that just forbids the parties from cheating full stop, just like in the classical world, but with this perfect unconditional security that quantum brings you. So there's a lot of theoretical work to push the protocol and its security proof into finding a better way of implementing it that would give you lower cheating probabilities and that wouldn't force you to implement this cheat sensitive or this deterrent factor, if this makes sense. So there's this theoretical aspect of the research, and then experimentally, of course, just improving the setups and the technology to get less losses, to have better visibility, such that the abort probability of the protocol decreases as well. So there's really like an interplay between the theory and the experiment. And I think these are the two main open points, or the two main directions.
If we focus for another few minutes on the experimental setup,
Mm-hmm.
are there any parts of the experimental setup right now? I can actually flip to that image as well, because there's quite a few components that are involved in the setup. So we can see it here.
Sure.
Are there any particular aspects of this setup that are particularly error prone as of now, and where you think, just from a hardware perspective, we could do better going forward?
Mm-hmm. Yes, so as regards to everything that leads to losses, there's a lot of experimental factors that can lead to losing a photon. This can really be improved in the future. So, for example, when we generate our photon, our single photon, that comes from a PPK-TP crystal, which is a nonlinear crystal that generates a pair of photons. This is done in free space. Of course, since this is a communication in a distance protocol, we have to couple this photon into an optical fiber. And that's where, to start with, a lot of losses can happen. So if you couple your photon better, if you have better optics and better strategies to couple it, you can gain in your transmission, and so you lower your abort probability. Then on the side of the detectors, single photon detectors, these are constantly being improved by all the companies that manufacture them and that sell them to us. Every year they're basically getting better and better and better detection efficiencies. So this also would scale the abort probability of the protocol down. Another very, very lossy component is this optical switch that allows basically the photon to be routed to different paths depending on Bob's outcome. This is also something that usually the faster the switch is, the more lossy it is. And so by improving this technology, this could also yield much better results, basically.
Okay. Is there any one of these three that is particularly lossy? Like, my takeaway from earlier was that the photon detectors, while they are constantly being improved, are already sort of at the stage where they're accurate enough so that improving them wouldn't cause huge difference in protocol accuracy. Is there a big discrepancy in these three components? Like, which one is most lossy? Or
in the case
roughly the same?
No, in the case of this experiment, I would say the optical switch is the most lossy component. As you say, single photon detectors, now the nanowire technology really allows you to reach efficiencies probably between 80 and 90%, sometimes 95%. So that's really starting to be very close to 1. So the coupling and the optical switch are definitely more dominant loss factors than the detectors themselves, for example.
Do you know of any potential architectures that could be built that wouldn't rely on having such an optical switch? Do you see this as a necessary component also if you were to do, like, say, a second experiment? Or do you have potential ways that you can circumvent using these components in the first place?
So that's a good question. That all boils down to actually designing the protocol in a smarter way, if we find a smarter way. There is a way already to do this protocol through strong coin flipping. If you have a strong coin flipping protocol, which previous implementations of quantum strong coin flipping do not actually require optical switches, strong coin flipping can give you weak coin flipping. Only, of course, since quantum strong coin flipping is not possible, even in the perfect scenario with 0 cheating probability or 50% cheating probability, this will never give you a perfect weak coin flipping protocol. So if you tolerate some bias on the cheating probability from your weak coin flipping, you can actually build it from a strong coin flipping protocol, which is done without an optical switch, which is much more loss tolerant. But this will never bring you to a weak coin flipping protocol with arbitrary low cheating probability.
Mm-hmm. Okay, I think I understand.
Yes.
Yes. Okay, great. In terms of the architecture, are there any other differences that you would build? Like if you had a round 2 of using this, not just cutting out individual components, but overall on the architectural side, are there any different setups that are being investigated that are sort of theorized, but where you don't yet have a physical implementation yet? Do you know of any other ways that this could potentially be done going forward?
Actually, we before publishing with this article, we also published a theoretical proposal for practical quantum weak coin flipping. And when we thought about developing this protocol, we really tried a lot of different architectures and simulated the cheating probabilities and everything. And actually, it turns out this particular architecture is the only one that we found can guarantee some form of security for weak coin flipping. It does not mean that we've tried everything, but at least to my knowledge until now, we did not find any better architecture. As a matter of fact, in order to lower the bias of the protocol, the cheating probability, the kind of brute force way of doing it right now would be to have more beam splitters than these 3 beam splitters. And actually, if you have the sort of very long sequence of beam splitters and you allow the photon to kind of bounce between Alice and Bob back and forth for a lot of rounds, then this should be able to lower the bias. But as you can imagine, this would increase the losses more and more and more. So to the best of my knowledge and my knowledge of the field, this is the only architecture so far, but I really hope that we can find some other architecture.
Mm-hmm. Perfect. I think as far as my questions go on the paper, we're bringing it to a close. I don't know if from your perspective there are any sort of asks that you would have from the wider industry, something you would like to see in the space, like related to this research that you think needs more attention than it currently receives, or anything as a sort of follow-up from this where you would direct the industry in general?
Well, as a general message, as you probably know, quantum technology and quantum cryptography right now is very, very, very focused on quantum key distribution. This is a protocol where Alice and Bob can exchange a secure key over a public eavesdropped channel, thanks to the laws of quantum mechanics. And this is truly the most mature quantum cryptography protocol, and it's actually entered the industrial realm many years ago, and it's being commercialized. My main message would be that there are a lot of applications that you cannot secure by sharing a key, so whether it's symmetric or asymmetric protocols. And now that quantum key distribution has shown such maturity and success, we should really focus on these new primitives like weak coin flipping, strong coin flipping, bit commitment, zero knowledge proofs that can give you other forms of security. So I would say that now that we've shown quantum key distribution is very successful and can give some higher security guarantees, we should focus really on these other protocols. And weak coin flipping is just one example of this. But we should really explore more how quantum can guarantee security for other primitives than key distribution.
Perfect. Then Mathieu, thank you very much for taking the time. I think this was super interesting, and I'm glad that we got to do this.
Thank you very much for inviting me.